Introduction to Venn diagrams. So let's begin our exploration of Venn diagrams. This slide serves as our introduction to the topic. First, the title asks, what are Venn diagrams? Well, Venn diagrams are essentially visual tools. Think of them as pictures that mathematicians use to show sets and how those sets relate to each other. Now, what exactly is a set? A set is simply a collection of distinct objects. By distinct, we mean each object is unique. These objects can be absolutely anything: numbers, letters, shapes, even other sets. For example, a set could be the numbers 1, 2, and 3, or it could be the letters A, B, and C. The real power of Venn diagrams comes from how they help us visualize the connections between these sets. They make it much easier to see how sets overlap, meaning they share common elements, how they differ, and how they relate to each other in general. This will be particularly useful when we start solving problems involving these sets, as we'll see in later slides. Finally, just a bit of historical context. These diagrams are named after John Venn, a British mathematician who first introduced them back in 1880. So, when you see a Venn diagram, remember it's a tool developed by a mathematician to help us understand and organize information. In the next few slides, we'll delve deeper into why we use Venn diagrams and how to construct them, building on this foundational understanding. Why use Venn diagrams? So now that we've established what Venn diagrams are, those visual tools for showing sets and their relationships, let's talk about why we bother using them. This slide outlines the key benefits. Venn diagrams really help us organize information. Think about it. Instead of just listing a bunch of facts or items, we can neatly categorize them into clear, visual groups. This makes it much easier to see the bigger picture and understand how everything fits together. Next, we have comparison. One of the biggest strengths of Venn diagrams is their ability to let us easily compare and contrast different sets. By visually seeing what elements sets have in common and what makes them unique, we can quickly identify similarities and differences. This is incredibly useful when you're analyzing data or making decisions. Moving on to problem solving. Venn diagrams aren't just pretty pictures, they're powerful tools for solving problems. They're frequently used in areas like set theory, which is the mathematical study of sets, but also in logic and probability. We'll see later how they can help us calculate probabilities and solve logical puzzles. Finally, clarity. Ultimately, Venn diagrams provide a clear and concise way to represent complex relationships. Sometimes, trying to explain relationships with just words can be confusing. A well-constructed Venn diagram cuts through the confusion and presents the information in a way that's easy to understand at a glance. So keep these benefits in mind as we move forward. In the next slide, we'll start diving into the basic components that make up a Venn diagram, like the universal set and the elements within each set. Basic concepts. So now we're moving on to the fundamental building blocks of Venn diagrams, the basic concepts. Let's break these down one by one. Now, what is a universal set? Simply put, it's the set that contains absolutely everything we're interested in for a particular problem. It encompasses all possible elements under consideration. Visually, we represent this universal set with a rectangle. Think of it as the outer boundary of our diagram. Everything inside that rectangle is part of our world for this problem. It's like saying, for this question, we're only talking about things within this box. Next, we have sets themselves. Remember from the first slide, a set is just a collection of distinct objects. These are the groups we want to compare and contrast. In a Venn diagram, we represent these sets as circles. And importantly, these circles are drawn inside the rectangle, representing the universal set. This shows that each set is a part of the larger universal set. So, if we were comparing students who like math and students who like science, each of those groups, math students and science students, would be a circle within the larger rectangle of all students in the school. Finally, we have elements. These are the individual items within a set. They could be numbers, letters, people, objects, anything. For example, if our set A is the set of even numbers, then 2, 4, and 6 would be elements of that set. They are the specific things that belong to a particular group. Understanding these three concepts, the universal set, sets, and elements, is crucial because they form the foundation for constructing and interpreting any Venn diagram. We'll see how these all come together in the next slide with a concrete example where we actually draw a diagram and fill it in. So, make sure you have a good grasp of these definitions before we move on. Example, representing sets of numbers. So now let's put everything we've learned about Venn diagrams into practice with a concrete example. First, we're going to consider two sets. Set A, which we denote as A, is the set containing the first 5 positive integers. That means A includes the numbers 1, 2, 3, 4, and 5. We write this as A equals the set containing 1, 2, 3, 4, and 5, enclosed in curly braces. Next, we have set B, denoted as B, which is the set of the first 4 positive even integers. So, B includes the numbers 2, 4, 6, and 8. Again, we write this as B equals the set containing 2, 4, 6, and 8, also enclosed in curly braces. Now, let's represent these sets using a Venn diagram. The first step is to draw a rectangle. Remember from the previous slides, this rectangle represents our universal set, denoted as U. In this case, we're defining our universal set as all positive integers less than 10. So, U includes the numbers 1, 2, 3, 4, 5, 6, 7, 8, and 9. Next, inside this rectangle, we draw 2 overlapping circles. These circles represent our sets A and B. Make sure they overlap because there might be some elements that are common to both sets. Label one circle A and the other B so we know which is which. Now comes the important part, filling in the diagram. The overlapping region, where the 2 circles intersect, represents the elements that are both in set A and set B. Looking at our sets, we can see that the numbers 2 and 4 are present in both A and B, so we write 2 and 4 in the overlapping region of the Venn diagram. Next, we fill in the remaining parts of the circles. We need to write the elements that are only in set A, that is, the elements in A that are not also in B. Those are 1, 3, and 5. So, we write 1, 3, and 5 in the part of circle A that doesn't overlap with circle B. Similarly, we write the elements that are only in set B, that is, the elements in B that are not also in A. Those are 6 and 8. So, we write 6 and 8 in the part of circle B that doesn't overlap with circle A. Finally, we need to account for any elements in our universal set that are not in either A or B. Looking at our universal set, which is 1 through 9, we see that the numbers 7 and 9 are not present in either set A or set B. Therefore, we write 7 and 9 outside the circles, but still inside the rectangle representing the universal set. And that's it. We've successfully represented sets A and B using a Venn diagram. This visual representation clearly shows us the relationship between the two sets, the elements they have in common, and the elements that are unique to each set. Remember this example as we move forward, because we'll be building on these concepts in the next slides. Key takeaways. First, remember that Venn diagrams are simply visual ways to show what sets are and how they relate to each other. They aren't about complicated calculations, but about organizing information so we can see the relationships clearly. Next, we discuss the universal set. This is absolutely crucial. The universal set contains everything we're working with in a particular problem. It's like the boundaries of our discussion. Anything outside of it isn't relevant to what we're currently analyzing. Remember, we represented this with a rectangle in our example. Now, let's talk about what happens when the circles overlap. That overlapping area isn't just for show. It represents the elements that are present in more than one of our sets. In the example we worked through, the overlap showed us the numbers that were in both set A and set B, the common elements. Finally, the parts of the circles that don't overlap are equally important. These non-overlapping regions show us the elements that are unique to each individual set. They belong to that set only and aren't found in any of the other sets we're considering. let's recap what we've learned about Venn diagrams with these key takeaways. Keep these ideas in mind, because in the next section, we'll look at some common mistakes students make when drawing and interpreting Venn diagrams. Understanding these key takeaways will help you avoid those pitfalls and confidently tackle more complex problems involving sets and probability. Common mistakes. Remember from the previous slides, the universal set, we called it U, is everything we're considering in a particular problem. It's the big picture. And in our diagrams, we represent that with a rectangle. It's super easy to get caught up in just drawing the circles for your specific sets, but leaving out the rectangle is a mistake. The rectangle provides the context. It shows us everything that could potentially be part of our discussion, even if it isn't directly in one of our named sets. Think of it like this. If you're sorting fruits, the universal set might be all the fruits you have, while your sets might be apples and oranges. You need to know you have a total collection to begin with. Always remember to include the rectangle representing the universal set. This provides context for all the elements. This is where careful thinking comes in. Before you write an element, a number, a letter, whatever it is, into a Venn diagram, you must ask yourself, does this element belong to set A? Does it belong to set B? Does it belong to both? Or does it belong to neither? If it's in both, it goes in the overlapping region. If it's only in A, it goes in the part of circle A that doesn't overlap. If it's in neither, it goes outside the circles, but inside the rectangle representing the universal set. Taking a moment to think through this for each element will save you a lot of frustration. Finally, let's talk about not labeling. This might seem obvious, but it's a surprisingly common error. Always label your sets, A, B, C, whatever you're using, and don't forget to label the universal set as U. Clear labeling makes your diagram understandable, not just to others, but also to yourself when you come back to it later. It prevents confusion and ensures you can easily interpret the information presented. So now we're moving on to some common pitfalls students often encounter when working with Venn diagrams. This is really important to get right, so pay close attention. So, keep these 3 things in mind as you practice, and you'll be well on your way to mastering Venn diagrams. In the next steps, we'll start looking at more complex scenarios and how to use Venn diagrams to solve actual problems.